So question 5 comes from paper 2, 2018, also question 5 on that paper. And we're asked to use the Newton-Raphson method. We've got to show that the formula can be written in the form given. It says it explicitly, the Newton-Raphson method has to be used. So I've written down already the Newton-Raphson method from the formula booklet as it's presented. To set it up, all we need to do is find the derivative of the function, because as you'll note or notice, the denominator here is the derivative of the function. Now, let's just define the function first, which we can see in the opening sentence. So 2x cubed plus x squared minus 1. So let's f of x equal 2x cubed plus x squared subtract 1, which we also know is equal to 0. It's got to be in that form because the Newton-Raphson method states so here. Okay, let's find the derivative. So differentiate each term separately. So we're going to have 3 times 2, which is 6x squared plus 2x, and the constant term vanishes. We can now put all this into the Newton-Raphson formula. I'm just going to move up here to do that. So we're going to have x of n plus 1 with the subscript there is equal to xn subtract the function. So in the numerator, I'm going to put the function in brackets so I don't make a sign error. So it's going to be 2xn cubed plus xn squared subtract 1 divided by the derivative, which I've just found, which is going to be 6xn squared plus 2xn. Okay, now that's it, but we have to write it in this particular way. We've got to write it as a single fraction as it's stated here. So we need a common denominator. So the left-hand side is fine, nothing to do there, but we need to write the left-hand term on the right-hand side over the common denominator, which will be 6xn squared plus 2xn. So it's going to be as follows. It's going to be xn multiplied by 6xn squared plus 2xn subtract 2xn cubed plus xn squared subtract 1, and that's going to be all over 6xn squared plus 2xn. Now, expanding and simplifying, we're going to get 6xn cubed plus 2xn squared subtract 2xn cubed. Watch out for the negative sign. Subtract xn squared plus 1, because we have a double negative, all over same denominator, 6xn squared plus 2xn. Now, collecting like terms in the numerator, we have got 6 lots of xn cubed there. Let's take away 2 lots of xn cubed there. So that's going to give me 4xn cubed. So looking good so far. Collecting some more like terms, we have 2 lots of xn squared, subtract 1 lot of xn squared. So that's just going to give me 1xn squared. Okay, and then the plus 1 remains all over 6xn squared plus 2xn. Okay, as required. So that bit's done. For the next part, we have to use the formula to find the values of x2 and x3. Now, just very quickly, you're going to have to show a little bit of working here, and it's not always clear how much you need to show. Because it's an iterative formula, if x1 equals 1, then to generate x2, we have to sub in x1 into the right-hand side. Okay, so it's going to look like this. Now that means that if x1 equals 1, we're going to have 4 lots of 1 cubed plus 1 squared plus 1 over 6 lots of 1 squared plus 2 lots of 1. Okay, so you can do that pretty easily. Looking at that, you're going to have 4 plus 1, which is 5, plus another one, which is 6. And then divide that by 6 plus 2, which is 8, which obviously is going to simplify to 3 over 4. So you can do that without using a calculator if necessary. That's going to be your x2. Now, to get the x3, you're going to have to substitute the 3/4 that you've just found, which is your x2. You're going to have to substitute that back into the iterative formula. Okay. Now, if you want to do this on your calculator and do it quickly multiple times, you can do it the following way. So I'm just going to pull up the calculator. Let's move it across to the other side. Now, if we're starting with x1 is 1, if we put in 1 and then press equals, that becomes your answer, okay, when it appears in the bottom right of the calculator screen, okay? Now, what we can then do is we can then tell the calculator to substitute that into the formula. So what we do is we say, okay, the formula is going to look like this. So we open a bracket and we say 4 multiplied by the answer cubed, okay, plus the answer squared, plus 1, close that, that's the numerator. Divide that by, open another bracket, and we've got 6 multiplied by the answer squared, plus 2 multiplied by the answer. Close that bracket. And then if we press equals, we get the 3/4 that we've just figured out just by putting the numbers in ourselves without using the calculator. Now, what's good is if I press the equals again on the calculator, that will generate the next term. So that means that x3 is done for us without doing any extra work. So using the class whiz, x3 would equal 2 over 3. And then if it asks for multiple terms, so x4, x5, you just keep pressing equals and it would do it for you. So, okay, and so on and so on. So that's using the calculator, okay? That it's all explained in the numerical methods lesson on the Newton-Raphson method. Okay, so we've got x2 and x3. Now, for a bonus mark, it says explain why for this question, the Newton-Raphson method cannot be used with x1 equals 0. Well, the main issue with the Newton-Raphson method, which again is explained in some detail, is this issue of the derivative, okay? There are conditions on the derivative that can cause problems. So if this denominator here, which is the derivative, is equal to 0, okay? So in other words, when f dash x of your function is equal to 0, that means that the Newton-Raphson method is not valid because you'll have a horizontal tangent and it's all based on the tangent iteratively approaching that root. So we have to say, if you're using x1 equals 0, that would mean that you would have 6 lots of x1 squared plus 2 lots of x1, which is 0, which is not allowed because the gradient function is not allowed to be 0. Okay. You could also state something like this would give you a horizontal tangent. Okay, so it's 1 mark, and it's just showing that you understand this limitation of the Newton-Raphson method.